you can notice that we're actually going to import now not just the linear regression model, but also from sklearn linear model, something called Ridge, which is Ridge regression. Here we simulate exactly the same data as we did before, and we create the same polynomial features. Now, our function for doing regression is almost identical to how it was before, except that over here in the model, instead of calling linear_regression, we call Ridge. As discussed in the videos, the lambda penalty is referred to here as alpha, which is somewhat confusing. The amount of the penalty we're actually going to pass to the function, and we're going to see what happens to our fitted model when we pass different amounts of penalty. Now, you should know what to expect. If we pass a huge penalty, then we should end up with a model which is literally just an intercept model, which will be a flat line. If we pass a penalty which is close to zero, we will get an incredibly complicated model, and if we pass a penalty somewhere in between, we should get, if we're lucky, a sensible model. So here we are. This is a function for fitting ridge regression. We're passing it our training data, 15-degree polynomial. So here we are. Our function for fitting ridge regression, we pass it the training data. It's going to be a degree 15. So if we didn't do any penalization or regularization, we would end up with a crazy complex model. And what we're going to do to start off with is only pass a very small penalty. What should happen? We should get exactly the same model that we had when we were just doing ordinary linear regression. You can see massive positive coefficient here, and then the massive negative coefficient that follows, and so on. What are the predictions going to look like? Very squiggly. You can see we've plotted what it would look like on the test data, and it's useless. Now what happens if we have a very large penalty? 1 times 10 to the 10. The coefficients, if you look carefully, they're all approximately 0. What are the predictions going to look like? A flat line, because the penalty for having a coefficient of any magnitude was so huge. Gradient descent, when trying to get to the bottom of the loss function, just simply set all the coefficients to 0. And even although the sum of squared errors was still large, it was better than having non-zero coefficients. Finally, how about we do something in the middle? 1 times 10 to the minus 3. Well, would you believe it? You get a beautiful function. If you look at it over the test data, that is really not bad. It's clearly not getting it quite right in the corner over there, but it's absolutely astonishing how choosing the right value for lambda has simplified the complex model. So whilst it's still using all 15 engineered polynomial features, we're still getting a appropriately simplified model. You may ask yourself, how did I choose that lot over there? Well, I could either go through this horrible bit of code down here, but I really don't fancy doing that. So instead, we're going to look at another notebook, Amy's house pricing. We're going to do the same thing there, and we're going to see how we might choose an appropriate lambda.